Okay, hello everyone, and welcome to the second exercise session of the Multiphysical Simulation 1 course. So today our topic will be this example here. Looks quite easy, and well, it is quite easy, and we will go through it step by step. So the PDE we're solving here today, or we're setting up, is the heat conduction equation in 2D. So in the lecture, I've seen you have already discussed the electrostatics equation, and this is the same type of PDE, just with a different interpretation of the material parameter. So the material parameter in this case, in the heat conduction, is the heat conductivity, or heat conduction coefficient, instead of the permittivity. And the right hand side is not a charge density. In the heat conduction equation, it's a heat source density. So the setup we will or the domain we will be setting up today is this rectangular domain with dimensions a, b, and as always, we need boundary conditions, and we set Dirichlet boundary conditions at the left and at the right boundary. So we prescribe a temperature here at the left boundary of 25 degrees centigrade, and on the right, minus 10 degrees centigrade. And at the top and at the bottom boundary, we don't prescribe anything. And I think you have already heard that if you don't prescribe anything at the boundaries, this corresponds to a homogeneous Neumann boundary condition, which means there is no flux through the boundary. So in this case, the flux is the heat flux density, which is the negative gradient of the temperature. And no heat flux through the boundary means an adiabatic boundary, so a perfectly insulated boundary. Yes, so this is the heat conduction coefficient, the K parameter, which is the material parameter in the inside of this bulk material. Okay. Yeah, and now the following slides I've prepared as kind of a backup for you that you can scroll through and more or less read what I will be saying in the next few minutes. But instead of going through the slides, I will change to the virtual machine to give a live demonstration example, because I think it's more useful than just looking at the slides. So I have already uploaded the slides on Teach Center, as well as a zip folder containing the following files. So in the zip folder I've uploaded, there are these 3 files, and we will go through them step by step. So the first thing I will do is I will copy my copy the folder that I've downloaded into a more reasonable folder. Let's put it right in the home directory, and let's switch to the terminal. So Control Alt T opens a terminal, and we're navigating to this folder, first simulation folder. Okay, we have these 3 files. So the first file, the wall.journal, corresponds to our Coreform Qubit software, so the meshing software. The mat.xml contains all the material information we need for the simulation with OpenCFS, and simulation input.xml, kind of self-explaining, contains the simulation input definition, so that the kind of simulation we want to carry out and the type of post-processing results we want to get out of CFS. So we'll start with the first part. We will construct a mesh, or we'll start by first designing the computational domain, and then we'll be meshing it. So we do this by opening Coreform Qubit, so our preprocessor, and due to some unidentifiable graphics issues, we have to start it with the sudo command. So we have to use it as start it as a root user. Password is user. I think I can switch this to full screen. Yeah. Okay. And then you will hopefully see this window right here. And I'm always working side by side with the following. So if you click here on this journal editor, it opens this editor right here, this text editor, which is not just a simple text editor, but a qubit specific editor. And by opening the journal file that I've provided, the wall.journal, you have a backup if you define some commands and you destroy your mesh or your geometry, you can always go back to these commands and they will give you the correct geometry and mesh. So what am I doing here? So the first two lines are just resetting the whole GUI and the software, so we have a clean software every time we execute this script. And the way I'm personally using Coreform Qubit is the following. So I don't always remember the correct commands to, for example, create a surface, a rectangle with width and height and in the correct plane. That's an easy command, but there are more complicated ones. So I'm using a hybrid approach, which is a huge benefit of Coreform. So let's draw the geometry first. So you click on the geometry button. We want to create a geometry. And we don't want to create a 3D geometry, but only a 2D geometry, so a surface. And here you can select whether you already have some bounding curves that are bounding your surface to be created. Or in our case, we want to simply define a rectangle with a certain width and height. And the width was, what was the width? 1 and the height 0.5. So we're using SI consistent units. So no units to specify here because it's in meters anyway, since we're SI consistent. So width was 1 and height 0.5 in the set plane. So if we click apply here, you already see the command that was executed. So you see the geometry, of course, and the command that produced this geometry. So what I'm doing, or usually I'm doing when I create meshes or geometries, I copy this command and paste it in the journal file, which is exactly the command that I've already specified here. So this is quite a handy workflow, especially if you have some complicated 3D geometries and you need to cut it and define different mesh densities on all surfaces. Then this comes in really helpful because you don't have to remember all the commands. So now that we have created our geometry, we want to mesh it. And you can, again, either do it by by clicking through it. So we want to mesh a surface with automatic sizing, so you can define your like roughly the size here. If you click on the surface, you can already see the discretization of the boundaries, and if you change this bar here, it automatically changes the or shows you how it would discretize the boundary. Okay, let's say we're okay with this discretization. Then we need to apply this size. So let's say I'm okay with this density. Then we click apply size. Then I copy this command and paste it in here. Factor, okay. So in this case, in the example I've provided, I was using size factor 5. Here I'm using size factor 6, but that's totally arbitrary. So now I've applied the size, and now I want to mesh it. So simply click mesh, and you see the meshed geometry. And again, copy the command to the journal file. Now we have our mesh. So I will, after I went through the remaining part of the script, I will show you another way, an alternative way to define the mesh, especially a more professional way to define it, since this auto factor is not really useful, especially if you're considering eddy current problems where you want to resolve a boundary in a very fine way. This won't be very helpful. But let's go on at first. So now that we have our mesh, we need to define the boundaries and also the volume. So we assign, or we want to assign, names to the volume or the surface and the boundary in order to be able to refer to these surfaces and curves in OpenCFS. So what I want to do is, let's say, this line here, I want this line to have the name L left, and I want to assign in OpenCFS, so that's what I'm defining in the XML file. I want to say L left has a prescribed temperature of 25 degrees centigrade, and I can only do that by, or I can only do this if the nodes here, or the boundary, has a correct or a unique identifier. And this is what we're defining here for the curves. So for the lines, left and right, and for the bulk material, so for the interior region. Let's start with the interior region. The interior region we define as blocks. So if you click here, I think this is called analysis groups and materials. Then click on blocks and assign a surface. So I want to name this surface, or I want to give it a unique identifier. So we can simply click on the surface here, click apply, and we have the command block1 add surface 1, which is exactly the command that I've provided here. Now we can rename it. So we can specify the name L left, click apply, which gives me an error. So let's copy this command into the console. The reason why I've got the error is because this line already had an ID, and re-identifying is not possible. So this was the message in the error console. So we assign the name, and now you should, this was correct, S-wall, and we see this block here in the model tree. if you open this blocks, we see the S wall region as the whole interior region of this domain. And contrary to the volume region, or contrary to the bulk regions, to the interior, we need to define the boundaries as node sets. So this is this button here, node sets, and again click on the curve you want to assign an ID, in this case curve, and you will get these commands. So I will make the shortcut and execute these 4 lines. And now we have here in the node sets flyout the L left. So the nodes here are identified as with the identifier L left, and these ones as the identifier L right. Okay, now we're actually done. The only thing left to do is to export the file. And this is simply done by this command. So we're exporting a CDB file. So a CDB file is actually coming from ANSYS. So this CDB file is ANSYS conforming, and we are exporting it since we have a CDB reader in OpenCFS, so we can read this mesh file. Okay, now let's start with the with a more professional way to create meshes. So now let's assume we have an eddy current problem, and we want to resolve this line here and this line here in a finer way. So we want to have a grading towards these two boundaries, towards the upper and lower boundary. How can we do that? So clean our software, clean the session, then create the geometry. So this stays the same, but now we will follow a hierarchical approach. So the first thing we want to do is mesh the curves that are surrounding our surface. And we can do this by clicking here, mesh curves. Then we need to select the curves we want to mesh. So let's first mesh this one, and by clicking here and holding the Control button and clicking another curve, we can select several curves. And we want to maybe refine these two lines. So the proposed discretization is too coarse. How can we refine it? I can grab it. Okay. We click here on this flyout and choose intervals and bias. And the bias simply means, so I'm changing this bar here, and observe what's happening to the node distribution. It gets denser towards one side. I can also assign a dual bias, so I can say it gets finer towards this edge, and it shall also get refined towards the other edge. Then we get a symmetrical refinement. But this is not what we want. Here we want a uniform discretization. So we assign a bias factor of 1. So no grading. And we want to change the interval count. Let's say 5 is not enough. We want to have 20. Let's say, okay, we're fine with that. Apply size. So here is the command for discretizing these two curves, so curve 3 and curve 1 with 20 nodes. And the next command assigns, or would assign, a possible bias factor, which we don't need for these two curves. So I've copied this command here, pasting it, Now let's mesh these two curves. So I could either click on the GUI or simply say mesh curve 3, 1. Copy this command, paste it in the command window, and we have a mesh on the curves. Now we want to have these two curves meshed, but with a bias, so that we have a boundary layer towards this edge and towards the top edge. So let's do this. Select these two curves. Oh, wrong control. Okay. And let's say we only want to have 10 nodes, but now we assign a bias factor. So let's refine it in one direction and also in the other direction. Now it gets coarser in the middle of the specific curves, and they get denser, so the node distribution gets denser towards these two upper and lower boundaries. We click apply size. Then we get again the interval definition for these two curves, paste them, and now we also copy the bias factor. Okay. And again, mesh these two curves, mesh curve 4 and 2. So now we have our boundary for boundary curves defined, and Trellis is now, or Coreform Qubit is now able to mesh the interior in a structured way. So what I mean by that is if you click here and you can choose whatever sizing function you want, since we already have the sizing defined by our boundary, you can just click on the surface and click mesh. And the mesh is done. Looks really nice. We have a grading towards the upper and lower boundary, and it is structured. The structured mesh is always good, since no large deformations of elements and the degrees of freedom are way less than if you discretize it with an unstructured approach. So for example, with triangles, or in 3D with tetrahedrons, it might be easier to mesh it in an unstructured way, but the quality of your simulation is decreasing with an unstructured mesh. So a mesh looking really neatly structured like this one will always deliver better and faster results than an unstructured mesh. Okay, so let's go back to our initial definition of the mesh. So this is the original journal file that you can download. If you don't want to play around with Coreform, you simply click on this green button, so play the current file, and it works through it. So it defines the geometry, creates the mesh, assigns the blocks and node sets, and exports the CDB file. Okay, now we can close Coreform. We don't need to save it. And if we observe the content of the current directory, we have this wall.cdp here. So this is our mesh file, and Coreform creates this history.journal files on the fly as kind of a backup. So it creates intermediate snapshots of your current journal file and stores them as this history 01, 02, 03 journal files. So we can remove this journal file to prevent any confusion. Yes, we want to Yes. Okay, now let's investigate the material file. And we do this with our Eclipse IDE. And if you work through the setup of the virtual machine video, this is already familiar for you. Okay, let's include also the second video, show the slides from last week. So in the resources sections, I've pasted the link to the YouTube videos from last year. So the first video is obsolete. I have deleted it. So the setup of the virtual machine, it was more or less the same as this year's setup, only some minor differences regarding the share folder handling. So I've deleted this YouTube video and I've recorded a new one and pasted the link on the Teach Center course. Then you can follow this tutorial here, which explains the handling and setup of Eclipse. And let's just assume you have already watched that. I will do a quick setup. So we just click on New General Editing and Validating XML files. We use the default location, yes. Then we can delete these folders inside the XML project, and we add a new folder to our XML project, and we will be adding our simulation folder. Finish. Okay. So inside of the simulation folder, we see the journal file, the mesh file we've just created, and the material and simulation input file. Let's start with the material XML file. Yeah, this is the design view. You can click through this in a tree-like structure, or what I prefer is to have it as in source code. So this is XML code based on an XML scheme, which we get from our homepage. And here you can define different materials. So for every material you want to define, you need to create this material tag first. So the material tag starts here and ends here. And in this case, we assign, or we want to create a material with the name concrete, and we want to assign the material parameters for the heat conduction equation. So for the heat conduction equation, we need the material parameters of mass density, of the heat capacity, and the heat conductivity. So these three parameters are needed, which I think maybe you've already seen it in the lecture, the heat conduction equation, or only the electrostatics equation. Only the electrostatics. Okay. Okay, doesn't matter. So these three parameters are needed material parameters. Then let's jump right into the simulation input file. So again, this is an XML file. We're reading the scheme, so the skeleton of of this whole file from our homepage, and this XML file has different sections. So at first, we start with the file formats tag. This file formats tag includes the input and the output, as well as the material data definition. So what's the input of our simulation? Of course, it's the mesh file. And here we define that it's a CDB mesh file. We also have different mesh readers available in OpenCFS, but the one that is easiest to understand is this CDB file reader. And we're reading the mesh file wall.cdb. Then we also define the output format. CFS uses an H5 file format as an output. So once we perform the simulation, the .cfs file, so the result file, is an H5 format. I won't go into too much detail. If you're interested, just Google it. It's a hierarchical data structure. And we also want to have a text output available. So if you specify this tag text with a certain ID, we can assign later on some results such that they are exported as a text file. You don't need to do this for the HDF5 file, since this is our default output format. And what we're still missing was the material data file, which is specified here, and it has the name mat.xml. If this mat.xml is located somewhere else on your system, you need to specify the path to this file. In this case, it's in our simulation folder, and we don't need to change the path. Okay, then comes the next important tag, which is the domain tag. Here we specify the volume regions, and I specifically say volume regions because in OpenCFS the highest dimension of the mesh is called the volume region. So in our case, the surface is the highest dimension of the geometry, and in CFS it's internally called the volume region, although it's actually a surface. So we're reading the S wall region, and we assign this region the material concrete. So if we had some other regions, if our mesh was a little bit more complicated, maybe it could look like this. So S wall and some S, I don't know, water, and we need then to assign this assign the material water to this region, although we don't have the water defined in the mat.xml. So this would, if we want to use water instead of concrete, we would need to to define it here in the material XML file. So we would need to copy that, replace concrete with water, and assign the correct material parameters. So this is up to you. You need to define the material parameters. It's not like in some other commercial programs where you simply say it is water, and the software has a database where the properties of water are stored. No, you need to define that. Okay, so in this case we only have one volume region, so this S wall, and it has the material concrete. That's the end of our domain definition. And then comes the most important tag, the sequence step tag. So it starts here and is closed here. So it goes all the way to the very end. Now let's check out what this sequence step contains. So it first contains the analysis type. Here we want to perform a static analysis, so no time dependence, just a pure Laplacian problem or Poisson problem of the heat conduction equation. We also have a time-dependent solver, so this would then be specified as transient. We have a harmonic solver, a multi-harmonic solver if you want to perform nonlinear simulations in frequency domain, and also some solvers for or analysis types for buckling and eigenfrequency. Okay, but in this case, we're just using the static solver. And up until now, we did not define anything about the equation we're solving. So this is the part that comes next. That's the PDE list. And this PDE list actually contains all PDEs that we're able to solve. In this case, we're solving the heat conduction equation. If you perform a magnetic simulation, you exchange this tag here with magnetic. If you perform a mechanic analysis, you replace it with mechanic. And so this tag here specifies the kind of PDE we're solving. Then we need to tell the program or tell the software that we want to solve the heat conduction equation exactly on this region S wall. So this region definition here could differ from the one we defined here. So this is just in the domain section. These are just the domains we are reading from the mesh. So we could maybe if our mesh had several regions, S wall 2 and maybe S wall 3. So let's assume we have 3 different regions. We read all these 3 regions from the mesh file, but we only want to solve the heat conduction equation on the domain S wall. Then we simply need to define the region tag S-name wall here without the need of defining the other 2, since we only want to solve it on this domain here. So this comes in quite handy, for example, in multiphysical problems that we will encounter later on. You maybe want to solve a mechanical equation in one part of your domain, and in the other one, you simply want to simulate the acoustic propagation that a harmonic excitation of your mechanical device will produce. So you're solving the mechanical equation on, for example, S wall 2, and the wave propagation equation only on S wall 2. Then you can define the regions here. So let's go back to our default solution. So we want to solve the heat conduction equation on S wall. Then we need to define boundary conditions. And in this case, we set the value of the temperature on the domain boundary L left to a value of 25. And the temperature of the boundary L right to a value of minus 10 degrees centigrade. Okay. We also have different boundary conditions available, but since we're running out of time, I will skip the more complicated ones. We also have some flux boundary conditions where you can define a heat flux vector through the surface, but you will encounter this anyway in the first homework, and we will and I will show you another demonstration example where we specifically go into that detail. So now we have defined our boundary conditions. The last thing we need to do is to define which quantities we want to export. And in this case, we want to export the heat temperature, so the solution quantity, as a nodal result. Since we're using nodal finite elements, so Lagrangian finite elements, this is a node result, the temperature. Then the heat flux density is the negative gradient of the temperature. And I think in one of the next lectures you will discuss how to compute derivatives on one element. And the way you compute derivatives is by taking or by considering all the, let's say we have a quadrilateral, by considering the nodal quantities on the four edges, on the four corners, and compute the derivative of these four corner degrees of freedom together with their ansatz functions. And so the derivative quantity is always defined in an element. That's why this is called element result. So we want to store these two results in our HDF5 format, so into our field format. We don't need to specify the export type, since if you don't define anything, it's automatically exported as H5. Okay, now we can close that. We don't need to save it. You can use the default ones I've provided and perform a CFS simulation. So you type in CFS and the name of the simulation file without the XML ending. Enter. Now we have executed our first simulation. So this is just the header of our file, of our software. We're reading the parameter file, so the input file. We're creating the writers for the HDF5 file. We're reading the mesh. Then you see the different blocks that are read and node groups. We're creating the heat conduction PDE. We're solving it. We're finished solving. And now we can visualize the results. So let's observe the contents of this folder once again. Before we executed CFS input file, there was no folder results HDF5 and no folder history. So once we execute a CFS simulation, it automatically creates these two folders. So there is the history folder is empty. There's nothing inside, but there is something inside the results folder. So there is a simulation input.cfs. So this is the H5 file that I was talking about. So the result file, which is called a CFS file in our case. And we can quickly visualize this file by using ParaView and the file name. And we don't want to visualize the boundaries. We only want to visualize the volume region. So click apply. You can look at the mesh by clicking on surface with edges. That's our mesh. And let's visualize the temperature. So by clicking here on this flyout menu, you have the different outputs that are available. So there are some generic outputs from the mesh itself. So the element number, or since this is a VTK export, we also have the VTK block names and indices, and the heat flux density. This is our vector quantity, and the heat temperature, which is our solution quantity. If you click on heat temperature, here you can see on the left we have a temperature of 25 and on the right -10. So that's the nodal result. That's a scalar field. Now let's go to the vector field, so the heat flux, the negative gradient of the temperature. So what would we expect? We have a gradient from left to right, and we're expecting a constant value of this heat flux, which is also the case. So the magnitude is the same everywhere in the whole domain. And since this is a vector quantity, we can, for example, only look at the x magnitude or only at the y magnitude. So the y magnitude looks a bit odd because it's a very small value. So these are that's numerics that we're seeing here. Or we can visualize the vector field itself by clicking here on glyphs, and here in orientation array assign that all the arrows should be pointing in the direction of the quantity heat flux density. Click apply, and this is our vector field. It's not very spectacular, but it is something that we would expect. If we look again at the heat, at the temperature, we have a gradient. It's not changing in y direction. It only has an x component. Since the gradient, there is only a gradient in x direction. Okay, so now we went through the whole workflow of a CFS, OpenCFS simulation. So meshing with Coreform Qubit, simulating with OpenCFS, and post-processing, so looking at the results, visualizing the results in ParaView. So next time we will be performing a simulation of a parallel plate capacitor, so an electrostatic simulation, and I would highly recommend that you finish the setup of the virtual machine until next week, so that you can follow the demonstration examples. And if you encounter any issues, just feel free to write into the forum. Okay, I will stop the recording now.